Hi everyone. In this unit we've been talking about equilibrium, and we understand that at some point most reactions reach equilibrium, meaning that the concentrations of the reactants and the products remain steady. So we're able to calculate an equilibrium constant if we're given the equilibrium concentrations or the equilibrium partial pressures. But what if we are given a set of conditions that are not at equilibrium? Would we be able to calculate what are the final concentrations once the reaction has reached equilibrium? So for the next couple of videos, we are going to be doing examples of where we have to calculate the final equilibrium concentrations. And this is the first video to do that. It's a fairly simple example, but the steps are very important for us to follow. The way we're going to do this is using what's called an ice table or initial change equilibrium. Let's take a look at the first problem. We have a reaction Z, and they gave us a Kc. We know that equilibrium constants are temperature dependent. There's a specific equilibrium constant for every reaction at certain temperatures. What are the equilibrium concentrations? So we have a question mark for A, question mark for Z, but these are at equilibrium. If you initially have this much A, and it's a concentration, and this much Z. Okay. So the first thing is determine which direction is favored if the reaction is not at equilibrium, or if it's off equilibrium. In some cases, you'll be calculating a Q, a reaction quotient, and understanding is Q greater than or less than Kc. We could do that, but honestly, we have no product, and we know that for most reactions you will have some product and some reactants. An equilibrium will be established. So your intuition should be that the reaction will go forward. The reaction will go forward. Sometimes the reaction will go backwards, but we'll say the reaction is favored going forward initially until equilibrium is established. Okay. Like I said, you could also calculate QC. You know that QC in this case equals the concentration of Z over the concentration of A. But you notice that Z is 0 and A is 0.850, and that equals 0. And that means that QC is less than KC. We've done this in a previous video, this type of analysis. And that means the equilibrium or the reaction shifts to make QC bigger. So it shifts to the right to give us more products. I just want to double check. Is 0 divided by any number a valid mathematical expression? Okay, good. Okay, so it is 0. I was just confused whether I think it's dividing by 0 gives you a, yep, syntax error. Okay. All right. That's important because the next thing is we're going to set up what's called an ice table. To set up an ice table, this is how I would do it. There are several methods, but I go ahead and write the chemical equation with the equilibrium arrow. Okay, and just understand that both are aqueous. Okay, so we are, that QC is valid. We are using aqueous. You could also use gas, but you can't use solids and liquids. Remember that rule? Anyway, we have the I, or the initial. So initially, we're plugging in numbers, okay? We're plugging in 0.850 molar, and we should know that when it says no Z at the beginning, put a 0 right there. So this makes sense. the reaction will go to the right, meaning that we are going to lose A and gain B. We have to reach equilibrium. Okay, and equilibrium actually is greater than 1. So it looks like the products should be in greater quantity, right? Okay. Now, before we continue with our ice table, I just want to put a little note here for ice tables. Use, in almost all cases, you'll use either molarities or, if you're given partial pressures of gases, partial pressures of gases. Okay. I would warn you not to use moles and definitely do not use grams. Okay. But we're going to think of a molarity as a quantity. I know it's a concentration, but it's proportional to the quantity because this as moles per liter. Well, it's in the same round bottom flask. It's in the same container, so it's the liters is the same for A, oops, and Z. Oh man. Okay, this should be Z. I don't know why I put Z and not just use A and B. Okay, Z. Any other mistakes? Okay, good. Like I said, this you could think of it as an amount because molarity is proportional to the amount moles because the volume always stays the same in this reaction. The volume of the liquid, it's aqueous. Okay, enough about that. Let's go to change. ICE. It is important that we know that it shifts to the right, that the reaction will go forward, because what that tells me is that we're going to lose some amount of A. We're going to lose some amount of A, and based on the coefficients, every time we lose a certain amount of A, we gain a certain amount of Z. You could think of it, I'll literally say, if we lose X molarity of A, we're going to gain X molarity of C. Equilibrium. We're going to have to solve for X. But for equilibrium, okay, we had this much at the beginning, and we lose a certain amount that we don't know. Let's just, write that down. 0.850 molar minus X, and this is X. Okay, again, it's important that you get the signs correct. Since we're going in the forward direction, we're losing A and we're gaining Z. There will be other examples where we have a lot of Z and a little A, and when you calculate the Q, you'll realize that Q is greater than Kc, and we got to go in the reverse direction. Then, in that case, this will be minus X. Okay. We'll get more complicated, more challenging examples in the next 2 or 3 examples. Okay. So I'm not going to go through all the subtleties of an ice table. We'll see those in future videos. But now what do we do? Well, number 3, I'm labeling steps 1, 2, and 3. 3, we're going to use the equilibrium constant because Kc, so they said Kc is 24, okay? But I'm not going to do that. I want to set up the expression first. So for number 3, write expression. That's going to be super important when we get to more complicated examples. The expression is this, right? It's products over reactants raised to the power of the coefficient, but there is no coefficients for this reaction here, so that's good. That equals 24.0. And what is that? Well, we're going to substitute x on the top divided by 0.850 minus x, and then we solve for x. So I'm going to cross multiply 0.850 times 24. When you practice several of these ice tables, you are going to get pretty good at algebra. So this is 20.4 minus 24x equals x. We're going to bring this to the other side. 20.4 equals plus 24x on both sides. 25.0x, and x equals 20.4 divided by 25. 0.816. Remember, for this ice table, we're using molarity, so x is molarity. And that is the concentration of Z at equilibrium. So immediately we could put here the concentration of Z. Now to get the concentration of A, we just have to follow our ice table. Be confident that we set it up correctly. 0.850 minus 0.816. So the concentration of A is 0.034 molar equals concentration of A. Those are your two answers for the equilibrium concentration. And what can we do? You can substitute back, right? Z is 0.816 divided by 0.034, and we should get 24. Very neat technique. You're given some initial conditions, and you can predict how much of A we're going to lose, how much of Z we're going to gain, and ultimately get an X so that it satisfies this condition that the Kc is 24. In the next example, I'm just going to quickly flash this. Meet me in the next video. We have some more information, complications. Okay, more interesting, maybe I should say that. A more interesting problem coming up, for example.